Hello, good morning. Now we move to the mass transfer. Yeah, this is the last part of the transfer phenomena, the mass transfer. Okay, so we're gonna talk about this mass transfer for the rest 4 or 5 weeks that we have. I think 4 weeks. Yeah. After that, we're gonna have another exam for the mass transfer. Okay, so mass transfer is a bit different compared to the momentum and the heat. Yeah, so it's a bit different, and we have different terminology, and the concept is a bit different as well. Because the momentum and the heat is very similar, but the mass transfer is a bit different. But I will try to explain things to you so you will not feel confused about this concept of the mass transfer. Okay, so in the video that I gave you earlier, I explained the intro, yeah, the basic of the mass transfer, a very short introduction to the mass transfer. So that's basically all the equation, all the relationship that you're gonna use for to solve the mass transfer problem. But actually, if you want to learn more, if you want to look at the equation more, you can find how to get that equation, and yeah, maybe more explanation about the equation in the bird book if you want, and you can also ask me now. Okay, so now have you watched the video? Yeah, I think you already watched the video.
Yes, ma'am.
Yes. Okay, so if you already watched the video, this because this is very important. Yeah, the video is very important because this is the basic concept. Any of you haven't watched the video yet? Any of you? Okay, all good.
Yes, I
Yeah.
have, ma'am.
Stefania already watched the video.
Yes.
Okay, yeah, so good. Yeah, so I hope that all of you already watched the video. So we're gonna go through the basic concept very quickly now. After that, we go to the example. Yeah, example. Okay, it's for the mass transfer. Okay, yeah. So I want to ask you, what is the difference between rho I and Ci?
Rho I is the mass and Ci is the molar.
Correct. Yeah. So both of them is concentration. No need to be confused. Yeah. So both rho and C is the concentration, but rho is the mass. Yeah. Rho is the mass, or if you maybe write the units is gram per centimeter cubic. Okay. And the C is the molar. So basically, this is the mole per volume. Yeah. So both of them is concentration. Okay, but one in the form of mass and the other one is the form of in the form of molar. Yeah. Why do we have two kinds of concentration? Because in the mass transfer, both mass and molar concentration are equally important, and both of the concentration are used frequently in the real application. Yeah. So that's why we need to have, or we need to know about the mass concentration and molar concentration. Yeah. So basically, no need to be confused. Yeah. Both of them are concentration, but one in the form of mass and the other one is in the form of molar. Okay. And for the binary mixture, yeah, we only talk about binary mixture, no multi-component mixture. For the binary mixture, we have, of course, we can have rho A and rho B, and of course, we also can have Ca and Cb. Okay. The mass fraction is described as omega A and omega B. This is the mass fraction. Okay, and the mole fraction is described as Xa and Xb. Okay. Both the mass fraction and the molar fraction, if you sum that up, there will result 1. Okay. So omega A plus omega B is 1, Xa plus Xb is also 1. Okay, so the mole fraction of A plus mole fraction of B is 1. And mass fraction of A and plus mass fraction of B is 1 as well. Okay. And this is the law that we have, the Fick's law. Okay, this is the Fick's law. Okay, I want to ask you, what is the driving force for the mass transfer? If you look at this equation, what is the driving force for the mass transfer?
Difference in concentration.
So the driving force is the concentration gradient, yeah. Either it's the mass concentration gradient or the molar concentration gradient, yeah. So that's the driving force, yeah. So in the momentum, your driving force is the velocity, and for the heat transfer, your driving force is the temperature gradient, and for the mass transfer, the driving force is the concentration gradient, yeah, either mass concentration or molar concentration, yeah. So because we have mass concentration and molar concentration, we also need two symbols, yeah, two symbols to express the flux of A, yeah, the flux of A. Okay, so here we have lowercase j, yeah. So lowercase j is the flux of A, yeah, is the mass flux of A when we talk about that flux in terms of the mass concentration. And here we have uppercase J, capital J. So capital J is also the mass flux of A. Yeah, it's also the mass flux of A, but we use capital J when we talk about the mass flux of A in terms of molar concentration, when we have a molar concentration of A. Okay, so lowercase j and uppercase j is the same. Both of them is the mass flux of A. Okay, but the lowercase j is the mass flux of A when we have mass concentration of A. Okay. Other way to write the Fick's law is shown in this part. Okay, if we compare the equation on the left and the equation on the right, yeah, we can see that on the right we have rho and also c outside the differential, yeah, outside the differential. So because we move the rho and the c outside the differential, what's being the driving force is the mass fraction of A and the molar fraction of A. Okay, because we know that when we have rho times omega A equal to rho A, and also we know that total concentration times the mole fraction of A equal to concentration of A. Yeah, so that's just another way to write the Fick's law. Basically, it's the same. Okay, up to here. Oh, yeah, up to here. Any question? Up to this slide? Okay, no question, yeah. So basically the Fick's law is almost similar, yeah, almost similar with the Fourier law and the Newton laws of viscosity, yeah. It has constant, this is constant, and it has driving force, and also it has the distance, yeah, the distance of the transport. So basically it's the same. In the momentum transport, yeah, if you still remember, in the momentum transport, momentum is not only transported by the molecular motion, not only transported by the molecular movement, but also can be transported by the convective flow. Yeah, so in the momentum, you have this is the total, yeah, this is the total momentum transport. You have tau, molecular momentum transport, plus pressure, also molecular, plus rho Vv. This is the convective term. This is the convective term. Yeah. And also in the energy equation, you have total energy, and it has a lot of things. And you have Q, and then what is the convective part of the heat? I forget. What is the convective transport of the heat? What is the equation? I really forget. Do you still remember the convective part? Hello?
Miss,
Yes?
I think it is rho Cp
Rho Cp.
and then velocity average.
Yeah, I think so, yeah. So
Um,
it must be contain rho and v, but I forget the others, yeah.
oh, dt over d x or z, I think.
Yeah, okay. So basically that must be just the rho Cp v, yeah. Okay. And okay, so sorry, I really forget about the convective flow for the energy, really forget. And last for the mass, yeah, this is for the energy or heat, yeah, maybe just heat. And the last one is for the mass. Okay, mass can also be transported by convective flow, so it's not only by the molecular flow. Fick's law only stands for the molecular flow. Only account for the molecular transfer. So molecular transfer of the mass is often called as diffusion. Yeah, diffusion. So Fick's law only account for the diffusion side of the mass transfer. Yeah, but actually mass can also be transported by the convective flow as well. Okay, so in mass we also have what we call as the combined flux, combined mass flux. Okay, because the mass is not only be transported by the molecular transport but also by the convective flow. Okay, so basically, and I skip a bit. Okay, the combined flux is expressed as N. We have capital N and also the lowercase n. Okay, lowercase n is the mass flux when we talk about mass concentration, and the capital N is the molar flux when we talk about the molar concentration. Okay, so N basically is the combined flux. Yeah, it already take into account the molecular flux and also the convective flux. Okay. The correlation between N and J looks like this. Okay, so Na is the combined flux of A, Ja is the molecular flux of A. So this is the correlation. Yeah, if you look at this correlation is different with all the correlation we have before. Yeah, so in the momentum, in the heat transfer, the correlation of the combined heat or the combined momentum transfer doesn't look like this. Yeah, so the combined mass flux equations is a bit different, looks like this. Okay. Any question? No, okay. So basically that's the basic concept of the mass transfer. Yeah, you need to know we have molar concentration and mass concentration, and then you also need to know that the mass can be transported by molecular flux, which is the fixed law, and also by the combination of molecular flux and convective flux. Yeah. So when we have mass transported by the convective flux and the molecular flux, that's when we use the combined flux. Yeah, Na. Okay. Okay. Yeah. So actually, what we can measure in our real life application is the Na. The Ja, the molecular flux cannot be measured directly. Yeah. So it is very important to know the relationship between Na and Ja to solve all the mass transfer problem. Yeah. Okay. Yeah. Next, I want to explain a bit about the velocity. Okay. Now, yeah. So basically, if we have the mixture of A and B, we have the mixture of A and B. In some cases, that mixture is move. Yeah. So the mixture is not in stationary condition. It doesn't stay still. Okay. Application of this mass transport with mixture movement is, for example, distillation. Yeah, in distillation column, we have mass transfer phenomena, and of course, the liquid is not stationary. Yeah, in distillation column, you found that the liquid is moved. Yeah, either upwards or downwards. Right. Okay, so in when we have when we have a mixture that's moved, we can say that component A moves with the velocity of VA. Component B moves with the velocity of VB. Yeah, the velocity of A and B, they could be different. Yeah, velocity A can be faster than velocity B, and the velocity of A and B could be on different direction. Yeah, for example, maybe A move to this direction and B moves to this direction. Okay, so this velocity could be different in value and could be different in direction as well. Okay, what we call as mixture velocity is the average velocity of VA and VB. Yeah, so this is what we call as medium velocity. Okay, so for example, if we have a bigger glass filled with water, yeah, filled with water, and then we drop ink, we drop ink, just a drop of ink into this water. Yeah, a drop of ink into this water. What will happen? Hello?
It will spread.
Right. Ink will spread. Yeah, the ink will spread. That's what we call as diffusion. Yeah, the ink will diffuse through the water. Basically, the ink will spread, move here to any direction. Okay. Right. Now, in this case, if you realize that when the ink, when you have one molecule of ink move to this direction, yeah, one molecule of water will also move to the opposite direction to replace the place, of that ink molecule. Yeah, in this case, the A velocity and the B velocity is on the different direction. Yeah, so because A velocity and B velocity is in different direction, what you see with your eyes is that all the fluid inside this glass is stationary. It's not moving. Yeah, it's just there. Okay. Okay. But if we have another case, in other case, so if we have case when the velocity of one of the compound is significantly higher than the velocity of other compound, we can see that the fluid is moving. Yeah, we can see the fluid is flowing. Yeah, so the medium velocity can also express as the mass average velocity and also as the molar average velocity. Okay, for the mass average velocity we have v, only v, and for the molar average velocity we have v with star. Yeah, so how to calculate the mass average velocity or the molar average velocity is just by multiply the molar concentration with the velocity plus the molar concentration of B times the velocity of B divided by total concentration. Yeah, same things for the mass average velocity. Okay, so the component velocity is VA and VB. The medium velocity can be expressed as V or V star. Yeah, this one is for molar. This one is for mass concentration. And the actual velocity of component I is VI minus V or VI minus V star. Yeah, or I can write VA minus V, VB minus V, or VA minus V star, VB minus V star. Yeah, that's the actual velocity. Okay, so the actual velocity of A is the VA minus the medium velocity. Okay. Now, this is what's important. Yeah. The combined flux of A, yeah, the combined mass flux of A can also be expressed as CA times the VA. Yeah, sorry, it was molar flux. Yeah, this one is the combined mass flux of A can also be expressed as rho A times VA. So this equation is important as well. You need to know this equation. Yeah, what is VA? VA is the velocity of A. Yeah, just the velocity of A. Okay. Any question? No, yeah, I think it's clear enough. Okay. Now we can go directly. To the application of the mass transfer. Yeah, we can go directly to the application of the mass transfer. So in this class, we will discuss about steady state and unsteady state condition. Yeah, in steady state condition, the heat, the mass transfer is only affected, or only be changed by the influence of the space. Yeah, but in the unsteady state, we have also need to look at the time dimension. Yeah, means that the mass can be accumulated or deaccumulated according to the time. Okay, and we also yeah, this one very important. In this class, we only talk about medium that flows laminarly. We will not talk about medium that flows turbulently. Yeah. What else? I think that's all. Yeah. The rest is very similar with the momentum transport and the heat transport. Yeah. What makes the difference is only what is the combined flux in the mass transfer. Yeah, and then the mass transfer in molecular motion is governed by the Fick's law. What else? I think that's all. Yeah. Others is the same with the molecular and the heat transfer. Yeah, so when you try to solve the mass transfer or mass balance problem, the mass transfer problem, you can do it by constructing the mass balance, or later on we'll look at the table. Yeah, so first we will look at how to solve the mass transfer equation by using the mass balance. The mass balance equation, when we have steady state condition, looks like this. Yeah, A in minus A out plus A production of A by homogeneous reaction equal to 0. Yeah. If we have unsteady state condition, the right hand side of this equation is not 0. Yeah, but we have something there usually. Okay. We also need boundary condition later on to solve this balance. We will look at uh, what is the example of boundary condition later. Okay, I think all clear, yeah? I think it's still clear. Still okay? Okay, now next we will look at the first example of the mass transport. Yeah, so I already made a video and we can watch it together. And then every time you feel like confused, or if you want to ask question, you can just talk on your microphone, and then I will pause the video and we can discuss about that particular problem. Okay. Welcome back to the transfer phenomena class. Today, in this case, we have a diffusion through a stagnant gas film. Oh, can you hear it? Can you hear it clearly?
Yes, ma'am.
Okay. Here, we have liquid A. Liquid A is evaporating into the gas B. Here we have gas B. Now let's assume that there is a device that maintains the liquid level at Z equal to Z1. At the liquid gas interface, the gas phase concentration of A, expressed as the mole fraction, is XA1. This is the gas phase concentration corresponding to the equilibrium with the liquid at the interface. Here we have a gas stream of A and B. The gas stream has an A concentration of XA2. The gas stream flows slowly past the top of the tube to maintain the mole fraction of A at Z equal to Z2 is equal to XA2, and this value is constant. We can also assume that gas A and B is ideal, so the entire system is kept at constant temperature and also kept at constant pressure. Now our task is to determine the mole fraction profile of gas A between Z2 and Z1. What is the XA profile? Okay, the first thing we have to do is to write the shell mass balance. So we have mass of A in minus mass of A out plus the rate of production of A by homogeneous reaction equal to 0. Please note in this case we don't have homogeneous reactions, so this part is equal to 0. Yeah, this part can be cancelled out. So now we have to write what is the rate of mass A in. First, we have to draw the control volume. This is the control volume. So here I have NA in at Z and NA out at Z plus delta Z. So rate of mass of A in is NA at Z times the surface or the perpendicular cross section minus the NA at Z plus delta Z. This is the A out times this perpendicular area equal to 0. Please note that NA is the flux of A. So to have the rate of mass of A, we have to times the flux with the surface. Okay, now we can divide this equation by S delta Z. And we get dNA per dz equal to 0. Okay, now we have to remember that NA is the total rate of A. Okay, so we have to find out what is the relationship between NA and JA. So I can write like this. In this case, we have to remember that A is the gas and B is the, sorry, A is the vapor and B is the gas. Please remember that the gas is stationary. Okay, so NB equal to 0. So at last, I will have Na equal to Ja times, sorry, divide by 1 minus Xa. Okay, so last time we have. Okay, question, please.
Yes, ma'am. I don't get why the gas is stationary when there is a gas stream. Or is
Okay.
it?
Okay, yeah. So basically, what we are looking at, so what is our interest is just to look at the XA profile, XA profile between Z1 and Z2. Okay, so this is between Z1 and Z2, right? Between Z1 and Z2. So the gas stream of A and B is only moves at the top of the glass. Yeah, gas stream of A and B is only moves at the top of the glass. So basically, along the Z1 and Z2, the only things that moves upwards is only the A component. Yeah, it's only the A component. The A will move here to the gas stream, while all the gas B is stay still inside the uh, glass. Yeah, inside the glass here. Okay, is it clear? Or maybe
It's
still?
clear. Thank you, ma'am.
Okay, so let's continue.
Ma'am?
Yeah. Yes. Yes.
Ma'am, can I ask?
Yes.
So NB is 0 because it's stationary, right, ma'am?
Right.
Oh,
Right.
and can I ask again how we get the final NA equation equals JA over 1 minus
Okay.
X, ma'am?
Okay, yeah. So NB is stationary because all the gas stay in the glass, yeah. But the A component, because it's evaporating, it moves up here. Yeah, it moves up here. And if you look at the mole fraction in at the liquid vapor interface here, we have mole fraction of A as XA1. And at the gas stream of A and B here, and the gas stream, we have mole fraction of A as XA2. So it's clear that XA2 and XA1 have different value. Yeah, so because they have different value, it can become a driving force, and A can move up here. Yeah. Okay. So next question is how to get this equation. Yeah. So because NB is equal to 0, our equation become NA equal to JA plus N plus XA and A. Yeah. Then I move the XA and A to the left. Now I have NA minus XA and A equal to JA. Yeah. Then I can write NA in the bracket 1 minus XA equal to JA. And finally, I can have NA equal to JA divided by 1 minus XA. Is it clear? But if you still confused, I can use... Oh, okay. Yeah, but yeah, for the equation, if you feel confused, I can use the writing pad again to explain. Yeah, just ask me. Yeah. Oh, my question. Any of you confused why I write just S over here?
Because in and out it's have the same surface, ma'am. So
Correct. Yeah, correct. So in and out has exactly the same surface. Yeah, exactly the same surface. So I just write it as, yeah. If you want to write it as uh, PR square and PR square, it's okay as well. But eventually everything will be just cancel out. Yeah, not cancel out, but you will divide that surface anyway. So it will be disappear. Yeah. So no matter if you write as or if you want to write like the real surface, yeah, the real surface of the circle, yeah, to PR square, that's okay. Yeah. So if you write PR square here, you can divide this equation by PR square delta Z and find eventually you will get exactly the same equation like this. Yeah. Oh, and I forget in this equation, I forget to put minus here. Yeah. I should have put minus here. Yeah, because it's from Z to Z plus delta Z. Yeah. At Z minus at Z plus delta Z. So it should, I should have put minus here. Yeah. Okay, yeah. Next, continue. So last time we have NA equal to JA over 1 minus XA. Please remember that JA is minus diffusivity of A, B times the concentration dXA over dZ. Okay, that's JA. So NA is all of this divided by 1 minus XA. Okay, let's substitute this equation into oh sorry, I think I forgot the minus over there. Okay, equal to 0. Now what we have is minus d per dz times minus dab c over 1 minus xa times dxa over dz equal to 0. As the gas is ideal or can be assumed as ideal, so at constant pressure and temperature, the concentration must be constant as well. And the value of diffusivity of AB basically almost constant. So everything can go out of the bracket. So now I have dAB C d per dz dxa over 1 minus xa dz equal to 0. Okay. Now the diffusivity and concentration is a constant, and I can move it to the right side to get this equation. d per dz dxa over 1 minus xa dz equals to 0. Okay, the first integration for this part will give us dxa over 1 minus xa dz equal to constant 1. Okay, next we have another integration. It will give us c1z, z plus c2 equal to the 1 minus xa, put minus in front. Okay, so this is our final equation about the profile of xa over z. Now we need the boundary condition. We need two boundary conditions. The first one, at at z equal to z1, xa is xa1. The second boundary condition is at z equal to z2, xa is xa2. Okay, now using this boundary condition, you can solve this equation and get the final equation to determine the xa profile over z. That's all for now. Thank you and see you in the
Okay.
next video.
So yeah, if it's clear, maybe now we can try to do one exercise. Yeah. So you try to do one exercise. Yeah. Okay. So now we have a solid sphere. Yeah. So this is a solid sphere. This solid sphere is hanging in the air. Yeah. So this solid sphere is hanging in the air. Yeah, in the ambient air. And we can see that there is a sublimation of the solid sphere to the air. Yeah, so the actual case for this is, what is it, camper ya, camper, tahu camper kan ya, camper yang kapur barus itu ya. Ya, so ya ini contohnya adalah untuk camper ya. Jadi kita punya camper bulat, terus digantung, terus dia menyublim kan, makanya kita bisa cium baunya ya. So yeah, when we have a camper like that, yeah, we can smell the scent of that camper because the camper undergoes sublimation. Yeah. So now, can you please explain, not explain, yeah, can you please determine what is the profile, yeah, what is the profile of the, let's say that this camper consists of compound A, yeah, so this camper is compound A, and the air is compound B, yeah, so this is the camper and the air is compound B. Now please determine what is the profile of A, in the air. Yeah, what is the profile of A in the air? profile of, okay, to make it consistent, yeah, to make it consistent, maybe the profile of XA, the profile of XA in the air. Okay, and to make it simple, just assume, that the radius of this camper is always constant. Yeah, so the radius is always constant. Okay, so the question is, what is the profile of XA in the air? Maybe 15 minutes. Yeah, try to solve this equation, this problem 15 minutes. After that we will discuss the answer. Yeah, please. Okay, let's discuss the problem. Yeah. Okay, so first thing we need to do is to draw the control volume. Yeah, so to draw the control volume, because the compound A is sublime to the outward direction, I will draw the control volume like this. Okay, this as R axis. So I have here is NA at R in and NA out at R plus delta R. Now let's write the mass balance. Yeah, the mass balance is NA in at R times the perpendicular cross section. What is the perpendicular cross section for this case?
For PR square.
Right. This one is 4 PR square minus NA out at R plus delta R times 4 PR square equal to 0. Yeah, and then we can divide everything by 4P delta R. Yeah, we cannot divide it by R. So what we have now is R square and A at R minus R square and A at R plus delta R divide by delta R equal to 0. Put limit and then we're gonna have minus dou R square and A over dr equal to 0. Am I correct? Agree?
Yes, ma'am.
Yes, ma'am. Then after this, we need to find out what is the relationship between NA and JA. Okay, NA equal to JA. Is it plus or negative? Is it? Forget.
It's supposed to be plus, ma'am.
Plus, okay. Plus XA NA plus NB. Okay. Yeah. And then let's have a look. NB. NB. The gas, the air is not moving. Yeah, the air is not moving. So NB is 0. Okay. But A, compound A is moving to that direction. So now what we have is NA equal to JA plus XA NA. Yeah. And then we have 1 minus xa and a equal to ja. Then we have na, ja divided by 1 minus xa. Okay? Now, substitute the ja with a fixed law. So now it will become minus dab c, what else? dxa over dz, right? 1 minus xa. Correct?
Ma'am, for the GAB, is it always over DZ, ma'am?
Oh, sorry. It should be over dr. Yeah, dr. Sorry. dr. Of course, it's not always over dz, yeah? So it depends. It depends whether you use Cartesian or spherical or cylindrical, and also most importantly, it depends on the direction of the movement, yeah, the direction of the transport. Okay, so is it correct now? Correct.
I
Okay.
do it like that, ma'am. Yes.
Okay. Others? How about the others?
Yes,
Okay,
ma'am.
agree. Stefania? Oh, Stefania has left the meeting. Yeah, maybe connection problem. Okay. Now substitute the n to this equation. What we're gonna have now is DAB C DAB C is going out, minus becomes positive, and then what else do I have here? D over dr dxa over 1, oh sorry, it's not really clear, 1 minus xa dr. Is it correct? Do I miss something?
Miss dr square, Miss.
dr square, where is the, oh yeah, dr square is missing. Yeah, correct. dr square, yeah, r square here, right? It's all good now? D over dr r square, yes, I think so, yeah, I think so. It's good now. Okay, now because the a, b, and c is a constant, yeah, the a, b, and c is constant, so let me rewrite the equation. Like this. Okay, now we need to do the first integration. The first integration will result on r squared dxa over 1 minus xa dr equal to c1. Correct? Hello?
Yes, ma'am.
Yes. So after this, what should we do?
Move r square and dr to the right hand side.
Okay. So we will get dxa
over 1 minus xa equal to is it c1 over r square, yeah, times dr. Okay, what's the result? What is the result for this equation if we do integration?
Ln 1 minus xa
1 minus xa. Don't forget to put minus in front. Equal to
equals to minus c1 over r plus c2.
okay. So we have minus of here, yeah. Okay, so is it correct?
Yes, ma'am. I got
Yes.
the same result as zeta.
Same? Okay, so you got the same results, yeah? Anyone got different results? Everyone got the same results? Okay. So if you all got the same results, now we need two boundary condition. Yeah, we need two boundary condition. What is our first boundary condition and what is our second boundary condition? So basically at r equal to something, at r equal to something, the xa is something, xa is something. Okay, so at r equal to, what is our first boundary condition?
0.
At r equal to 0, so that means at the center. Yeah, so our interest is to look at the A profile in the air over here. So we will not choose r equal to 0, yeah, because 0 is in the middle. Yeah, so first boundary condition, another try,
Equals to R.
equals to capital R. What is the xa?
XA1.
Yeah, you can write this one is xa1. Yeah, actually this question is actually open-ended. Yeah, open-ended. So our second boundary condition, any idea?
Capital R plus, for example, delta R, ma'am.
Or like this?
Is it? I don't know.
Yeah, we cannot put plus delta r because we never know what is the real value of delta r. Yeah, so for the boundary condition we really need to put something that we know the exact value, yeah, or at least we can measure. Yeah, so at least for the position for the r we need to put at r at a certain position that is exact. Yeah, so if we still put delta r a variable, it will not work. Yeah, so we need to put another value. Actually for this problem another boundary condition is at r infinite xa is 0. Yeah, actually what I said earlier, this equation is very 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 open-ended. Yeah, it's very open-ended. You can see, you can have a look at the boundary condition. It's very uncertain. Yeah, because this question is very very open-ended. Yeah, usually we always have uh, certain position and certain value. Yeah, at r equal to infinite xa equal to 0. Yeah, this is true physically, but will be very difficult to measure actually. Yeah, and usually at r equal to capital R, at the surface of the ball, usually the molar fraction of A can be assumed as 1. Yeah, so at the surface of the ball, usually we assume that we only have vapor, uh, vapor of A. Yeah, so at r equal to capital R, we can say that xa equal to 1.
and the other boundary condition is at r equal to infinite, xa is 0. Yeah. Okay. Any question? No, but actually it's very good. Yeah, you can solve this problem until you get the the equation, the final equation. Yeah, maybe for the boundary condition, yes, we still need a lot of practice for this mass transfer because, yeah, what I said earlier is a bit different compared to the previous topic. Yeah, but we will learn. But it's good for the first lecture of this mass transfer. You can already solve the problem. Yeah, it's good, very good. Okay, any question for today's lecture? No question? Okay, if you don't have,
Ma'am,
yes, please.
may I ask?
Sure.
So, NB is 0 because the air is like very large in volume compared to the sphere, or
Which one for the second boundary condition?
um actually the correlation between NA and JA.
N A N J. Oh, this one, yeah. Okay, this one.
Yes.
Okay, so actually, the NA always moves outwards. Yeah, always moves outwards. But the air, if we look macroscopically, the air just stay there. Yeah, but the A will move outward. Yeah. So how to explain? Yeah, actually, because A will be travel across here, and actually I like this. The A concentration at the surface of the ball will be high. Yeah, correct? Will be high. And the A concentration when we stand for we stand far enough from the ball will be very very low actually. XA here is low because they have uh, concentration gradient. A will move here, but the air will always have almost similar concentration. Actually, yes. At a certain position, for example, here, if we look at the concentration, we will have compound A high enough concentration, so the XB should be a bit low, yeah. And then over here, the XB will be high, and so on. But yes, because air is just has significantly higher volume than the A, than the compound A. So the air is can be assumed as stagnant. Just stay there.
All right. Thank you,
Thank
ma'am.
you. Another question?
Ma'am, can I ask?
Yeah.
So we should use the correlation like the combined flux NA equals CA times VA only if there's mixture movement.
Okay. Yes. So the correlation, this one, yeah, Na equal to Ca times Va. Yeah. So this correlation actually will only be used when we have mixture movement, right? Yeah. When we have mixture movement, when we have a convective flow.
Okay, ma'am, thank you.
You're welcome. So if you don't have convective flow, you don't need uh, you don't need to worry about this equation. Yeah, you will not use this equation if you don't have convective flux. If you don't have something flowing. Okay, maybe you have more question.
Ma'am, I want to
Yeah.
ask why the area is not written as just as like the last question, ma'am?
Okay, yeah. So basically, if you have a ball like this, okay, the area over here, the area over here, you can write it as 4pr square. Yeah, and then in our control volume, we have another line like this. Yeah, so the thickness is delta r. So actually, the area at the out position is 4p r plus delta r square. Even though delta r is very, very, very small, but still the area is a bit different. Yeah. In the previous example, this one, if I took cross section from above, yeah, if I took cross section from above the glass, it will looks like a circle. Yeah. Okay. Or maybe I just draw it like this. It's not a cross section, yeah. Now it's front section, yeah. Front view, yeah. This one is front view. So actually, in this case, the A is okay. A in from here and A out from here. The area is exactly the same. Yeah, the area in is is P r square, and out also at V r square. Yeah, exactly the same. But for this case, the area is actually a bit different. But we still put 4pr square over here just for simplification as always. Yeah, because delta r is very small. But actually the area is a bit different. Okay, is that clear?
Yes, ma'am. Thank you.
Okay, you're welcome. Do you still have question? Okay, so no question. If you don't have question, I have another link, yeah, in the MS Team for this problem. Yeah, for this problem. Please watch this problem before we have class tomorrow, and then if you have question about this problem, we can discuss it during the class. And if we still have more time, we can do another exercise. Yeah, because I think exercise is good. Yeah, it's good for you and for your understanding about this topic. Okay. Okay, then see you tomorrow. Have a nice day. Bye.